Okay, to continue with the talking about the motion of an object, we ended the last video with me asking you to consider what it would mean if the slope were steeper, or more generally, what does the slope represent for a position versus time graph? And I want to make sure I'm being clear about this. I wasn't asking about how steep the surface was that the cart was on. What I was trying to ask is how steep the slope is. So for example, the velocity of the cart in the y direction was represented by these blue dots, and I've got a blue line on there right now, sort of a line of best fit through those dots. And how steep it is it has no steepness. The slope of this is 0. What does it represent that the y position of the buggy never changed and the slope of this graph is 0? And what does it mean that in the x direction the slope is 0.1586 meters per second? Remember, the slope of an object is sometimes referred to as rise over run. Well, if you look on this graph, the vertical axis here, the rise, has units of meters, and the horizontal axis has units of seconds. So meters over seconds is part of the slope, and that is a little bit of a hint to us about what that slope represents. It represents something to do with the speed of the buggy. If I say the buggy is moving at 0.1586 meters per second, you would recognize that as a description of its speed. And I'm getting that number from the slope of the graph. If the buggy were going faster, it would have a larger rise for every segment of time that it runs on this graph. We would have a larger increase in the vertical direction than in the horizontal direction. So this green line here is what it would represent if the buggy were going much faster than what we saw it going across the screen. All right, let's make this a little bit more useful. Let's work with this concept that slope tells us something about the speed of the buggy. Let's take a look at how you find slope in the first place. The slope formula from algebra class, you might remember, is y2 minus y1 over x2 minus x1. That's how mathematicians refer to it, because they have these generic x and y axes that are just variable x and variable y. We're going to put our more specific variables in here. So remember, the horizontal axis was time and the vertical axis was the position. We're going to use the position in the x direction. So our slope of position versus time will be position 2 minus position 1 divided by time 2 minus time 1. And if we were calculating this by hand, you could take any 2 points on that graph or any 2 points out of my data table and use the position and time for one of those points and the position and time for another one of those points, and I'll calculate the slope. Algebraically, it would look like this. So the slope is x2 minus x1 over t2 minus t1. Remember, over here, the mathematicians are referring to x as just any variable on the horizontal axis. Here, I'm referring to x to mean the position of the object in a x spatial dimension, where space exists in x, y, and z. I want to remind you about this Greek letter delta, which you've probably seen in some science class or math class before, but it may have been years and years ago. So if you don't remember what exactly delta means change. Anytime you see the delta, we're going to use it a lot in physics class. If you see delta of something, if delta x means x2 minus x1, you need 2 values. And delta t is t2 minus t1. You need 2 values of whatever the variable is in order to calculate what the delta of that is. So is the object's speed the slope of the graph, delta x over delta t? Slightly more complicated than that. Let's talk about y. This is a piece of lab equipment that is called a motion sensor, and I have this video here. It's accidentally slow motion, but I think it'll be fine. The way this thing operates is on echolocation. You point this thing at it and it tells you how far away something is. The gold disc makes little clicking sounds, so the clicking sounds go out to the object and then they come back to the gold disc, and the computer can tell you how far away the object is that the gold disc is pointing at. It's just like sonar or the echolocation that bats use to navigate. As a rangefinder, this little device is okay, but its real value is that it can do this continuously, multiple times per second. It can tell me how far away an object is now, and now, and now, and now, which means I can create that into a data table with multiple times, and then I can make a graph from that data table. So for example, I put the sensor at the end of a track here, and I pushed a cart away from it, and then something happened off screen and the cart came back and actually crashed into my motion sensor. You're not supposed to let it do that. The graph of that little experiment that the motion detector made looks like this. Let's take a look at the final graph that it created. Your goal with a graph like this would be able to look at something like this and understand what the object that was being graphed did, even if you didn't see the video. So for example, there are clearly 4 regions on this graph. 1, 2, 3, and 4. In the first region, the position versus time graph here, I can see that the position is about 0.2 meters, and it doesn't change as time goes from 0 to about 1 second. What does it mean if the position doesn't change for the first second? That would mean that the buggy didn't go anywhere. So I could know that from this graph even if I hadn't seen the video. What happens in the next part of the graph is from 1 second out to about 3 seconds, we have this consistent up motion on the graph here. It is a linear graph pointed upwards. And in fact, if you go find the slope, it is 0.6912 meters per second. So at that point, it means that the buggy is traveling at 0.6912 meters per second. That's how fast it's going. Then over here in region 3, we see it is also linear, and I can find the slope of that. It's negative 0.5067 meters per second. The negative, what does that tell me about how fast the buggy's going? I believe that it's going 0.5067 meters per second, but what the negative means is maybe unclear at first. We want to make sure we can clear that up. And down here in region 4, we're back to the position is about 0.2 meters and it stays at about 0.2 meters. As you saw, it actually crashed right into the motion sensor, so it should have a position of 0. But the motion sensor doesn't understand distances less than 20 centimeters away from it, so it just says it's 0.2 meters. It's a little glitch in our experiment there. All right, if I watch this again, let's see if we can watch the video again and see all 4 segments of the graph mentally, even though we don't have it on the screen here, and figure out what that negative means in segment 3. So that's region 1 of the graph, region 2 of the graph, region 3 of the graph, region 4 of the graph. The difference between region 2 and region 3, if we go back and look at the graph, is that one of them has a slope that's positive and one of them has a slope that's negative. And then on the video, the difference was, in one case, the cart was moving away from the motion sensor, and in the other, it's moving back toward the motion sensor. That's what the negative tells us, is the direction of motion. That brings us to some terminology of motion. I am not going to quiz you on vocabulary, but you will get tricked if you don't know your terminology. So it's not that you should be memorizing this, but you do want to understand the difference between these different terms. The displacement of an object is where an object is now compared to where an object was earlier. It requires 2 measurements. In this case, we're calling them x1 and x2. That's for an object that is moving in what we're referring to as an x direction, which in the experiment was just back and forth on my track. In any problem that we do in class, we'll say left and right on the page is delta x. Delta x can be negative depending on which direction you are traveling. If this number, x2, is smaller than this number, x1, you get a negative number. A delta x being negative tells me that I am moving in a negative direction, which would mean to the left for any problem on the screen. A delta x that is positive means I'm moving to the right for any problem on the screen. And the y and the z here are grayed out because they exist and it works the same way. Y for up, down, z for out of the page, into the page. They're grayed out because we're not focusing on them right now. The distance an object has traveled is the total length of the path traveled between 2 positions. This cannot be negative. This just keeps adding up. So for example, if you get up, you get in your car, and you drive around the block, Your total displacement at the end is, here's where you are back at your house, here's where you started at your house, your displacement is 0. Your distance obviously wouldn't be because it has added up. We don't actually spend a lot of time talking about distance in this class, but we want to use it here to emphasize that it's a little bit different from displacement, even though they're both measured in meters. This idea that the slope of the graph of position versus time is the object's speed, we're going to complicate it a little bit right here because speed is an absolute value like distance and like time. It can't be negative. So I introduce instead this term velocity to say that an object has a rate at which it is changing its position and it has a direction that it's moving in that we're going to be specific about. Time can't be negative, but displacement can be. So if average velocity is the slope of a segment of a graph of position versus time for an object, I can imagine a slope that's positive and a slope that's negative, and I can interpret that a positive slope of position versus time means that an object has a positive velocity. It means it's moving in one direction. But if it has a negative slope on the graph, that means it's moving in the other direction. Okay, that makes sense. Algebraically, you would get the positive velocity or negative velocity by whatever the sign of your displacement is. And that should make sense. An object that's moving in a negative direction will have a negative displacement and therefore have a negative velocity. And all those negatives mean is it's moving to the left on our screen. The speed of an object is therefore the absolute value of the velocity. We refer to it as the magnitude of an object's velocity. That word magnitude will pop up, and what it means is there's a number and there's units, but we don't want a direction as part of this statement. So if you were asked for the velocity of an object, you are asked for the direction even if it doesn't say so. The word velocity means include a direction. The word speed means don't include a direction. It's not appropriate for this question. Okay, think back to the video. We take a look at this graph, and we had the 4 different regions on this graph, and these correspond to 4 different velocities. The cart initially had 0 meters per second velocity, then it had this positive velocity, 0.69 meters per second, then it had this negative velocity, 0.5067 meters per second, and then 0 meters per second down here. Velocity will be an important thing for us to talk about because it gives us information about what is happening to an object's position over time. I'd like you to think back to the video and ask yourself what caused the velocity to change from region 1 to region 2. The velocity here is the slope of this graph, it's 0. And the velocity here is the slope of this graph, it's suddenly positive. What happened to cause it to change? And then what happened up here to make the slope go from a positive value to a negative value? And then what happened down here to make the slope go from a negative value back to 0? We'll talk about that in the next video, and then we'll do some short example in a video after that.